In section 1.2, we're going to be looking at different kinds of views of rates of change. Sometimes we're going to be looking at an average rate of change. Sometimes we're going to be looking at the so-called instantaneous rate of change. We're also going to be looking at these in a couple of different forms. So what might a rate of change look like in a graph? What might a rate of change look like in an equation? What might a rate of change look like if we are dealing with a table of values? So in this video, I want to talk about estimating rates of change, or in some case finding rates of change using an equation. So I have the equation y equals x squared here, trying to stay kind of basic with this. It's a parabola. We're going to be looking at it in the region primarily between 1 and 4. So I've got that part of the graph here. Not majorly drawn to scale, but still enough of an image that we can kind of get an idea of what's going on here. So the first thing I'm asked to find here is the average rate of change. So remember that the average rate of change is the rate of change if the function had been linear. In other words, what kind of slope, remember rate of change is really a slope, what would the slope need to be to get from a starting point to an ending point if you were constantly going at the same slope? So we're looking at the interval from 1 to 4. And in fact, I don't even need this part of the graph. We're starting up here at x equals 1, and we're going to end over here at x equals 4. So when we're finding the average rate of change, you're really finding the slope of a secant segment. Okay, secant segment cuts through a curve. It's going to cut through the curve at x equals 1 and x equals 4. Okay. Again, the formula for that in function form, it's technically just a change in y over a change in x, but for the average rate of change, they usually write this using function notation. They'll write it as f of b minus f of a all over b minus a. All right. So in this particular example, you can see that we're starting out at f of 1, we're ending at f of 4, okay? Technically, this is the point 1, 1, and this is the point 4, comma 16, okay? So technically, if you just want to find the slope between those 2 points, that's what you're doing. Now, according to the formula, our b value is 4. We're starting at 4 and we're ending at 1. So we're technically finding f of 4 and we're subtracting f of 1, okay? That's going to be our change in y. And then our b value here is 4 and our a value is 1. So we're dividing by 4 minus 1. And again, this is really just a change in y divided by a change in x. Okay, so the functional value at 4 is 16. We're starting at 16. We're dropping down to a y value of 1. And then we're dividing by 4 minus 1. You're going to get 15 divided by 3, which is 5. Okay, so what does this mean? Well, I didn't give you a specific explanation what this graph was, but if we put this into some type of context, this would essentially be saying that, you know, if I was driving a car and this was a distance maybe in miles and a time, or maybe we have meters and seconds. If you found the slope, you would have a certain number of meters traveled in a certain number of seconds. And so this would be saying that that slope right there would be 5, meaning 5 meters per second is how fast you traveled, or how fast you would travel to get from this point to that point had you traveled at a constant pace. Now, the actual graph is sloped a lot less than this. It's not sloped very much here, and then it gets steeper and steeper and steeper, and actually gets steeper than that line over time. So when we talk about the instantaneous rate of change, we're talking about the slope at a particular point. Again, if this was a velocity and I took a photo, how fast would something be going, for example, at 2 seconds? Okay, that's what the instantaneous rate of change is. So for an equation, you actually have a lot of flexibility here. So if I'm trying to find the instantaneous rate of change, I'm trying to find the slope of the point right there. You can kind of imagine if you're riding in a roller coaster car, for example, it's basically the angle that your roller coaster car would be tilted at. What we actually talk about when we talk about the instantaneous rate of change, we say that the instantaneous rate of change is the slope at one point. We actually say that it's the slope of the tangent line to that point, okay? So if I have a line basically kind of following along here, what would its slope be at that particular point to just barely touch the curve in one point? All right, well, we can't get that value exactly, but we can get a pretty good estimate of it by picking some points that are really close to x equals 2. All right, so anytime you have a slope, you can't just use one point. Okay, you're always going to have to use 2 points, but we can kind of try to see a trend here. So I'm actually going to be using the average rate of change formula, but we're going to be finding the average rate for such a small interval that it's really going to be estimating the rate at an instant. Okay, so you'll notice here the formula isn't going to change. Now, it's a function, so I can really get any points I want for the function here. So what I'd like to do is, of course, we know that it starts out at the point 2 comma 4, and I'd like to pick a point really, really close to 2. So I'm going to pick a point like right here on the curve at like 2.1, okay? And I can put that into the function. 2.1 squared, I believe, is 4.41, right? Yes. So that's going to be the point 2.1, 4.41, okay? Now, I don't have to pick 2.1. I could pick like 2.2 or something, but you want points that are really, really close together, okay? And again, this point's not going to be on the tangent line. It's going to be on the curve, but it's still going to have a slope that's really close to what the slope of the tangent line would be. So anyway, we're finding the slope here between 2, 4, and 2.1, 4.41, okay? So that's change in y, 4.41 minus 4, over the change in x, 2.1 minus 2, and we get 0.41 divided by 0.1, which is going to be about a slope of 4.1. Okay, so that's a pretty good estimate. This is telling us this slope here would be about 4 at that point. Okay, now you don't have to use that point. You could go back behind this point a little bit. You could have gone maybe to the point here at 1.9 on the curve. I don't know, 19 squared? I should know that. Anyway, 1.9 squared is 3.61. So that's the point 1.9, 3.61. Okay, so we could do that instead. I could do 4 minus 3.61, okay, divided by 2 minus 1.9. And that's going to be 0.39 over 0.1, which is going to end up being 3.9. Okay, so notice that this line's not very steep at first, and it gets more steep over time. So if I go a little bit beyond the point and pick a point up here to the right, it's going to be a little bit steeper, a slope of about 4.1. If I go back a little bit, it's a little bit less steep. It's about 3.9. Now, some people would say the best overall slope, do we want points that are right before that point, or do we want points that are right after that point? A lot of people would say it would be a good idea to average those two values. Actually, if you average 4.1 and 3.9, you would get about 4. Okay, so that's one thing that you could do. Go a little bit beyond the point, a little bit behind the point, find your two separate slopes, average the two. You'll get a pretty good estimate, okay? Another approach you can use is to just try to keep picking points that are progressively closer to a particular point. For example, let's say I'm picking a point past 2 again. So I'm going to go back here. Let's say I've chosen a point at 2.01. Okay, 2.01 squared, which I do not know off the top of my head, is about 4.0401. Okay, and I can find the slope between those 2 points, and those would be even closer together, probably give me an even more accurate slope. So if I do 4.0401 minus 4, so y2 minus y1 over x2 minus x1, we've got 2.01 minus 2. We're going to get 0.0401 divided by 0.01. And remember, this slope here was 4.1. This slope here is going to be 4.01. So if we pick points a little bit closer, notice we get an answer that's a little bit closer to 4. And in fact, I could take this even a step further. I could pick a point like 2.001 and put that into the function. 2.001 squared is about 4.004001. Okay, so I could take 4.004001 minus 4 over 2.001 minus 2, and I would get 0.004001 over 0.001. If you work that out, it's going to be about 4.001, okay? So notice, my original estimate of my slope was about 4.1. I picked points a little bit closer together. And again, you could pick a point that's closer above it or behind it. You could have picked like a point at 1.99 here as well. But we got a slope that's a little bit closer to 4. I picked points that were a little bit closer together. I got a slope that's a little bit closer to 4, all right? This is the idea of a limit. We're getting closer and closer and closer to the actual slope. So a lot of times we're going to be able to kind of estimate this if it looks like it's approaching a whole number value. In other cases, you may not really be able to tell that it's approaching anything that you recognize, but you can pick points that are really close together and find the slope, and you'll get a very good estimate of what the slope would be at a set point, okay? So that's the distinction. Average rate of change, usually over a larger interval. The instantaneous rate of change, you want points real close together to try to figure out what would the slope be at a particular place on a curve.